Okay, everyone. So today we're gonna learn about again the what is optimum feed, and also a side stream, and also multiple feed. Yeah. Then let's put it full screen. Right. So yesterday we talked about how to construct the diagram. Let's have a little bit of review. Kevin, what should you do to construct the equilibrium stages for the distillation column?
What do you mean, Bu?
The step. What should you do first when we have an example? Okay, you have to construct equilibrium stages for distillation column. So what is your first step? What do you need?
Is it based on a graph, Bu?
Yeah, you can see this graph and then you can explain it, which one first that you have to put it.
Uh, Identify the intercept, I guess.
Yep, but before that you have to locate them first, yeah?
The XD, the XB, Bu.
Yeah, right. And then? Okay, so yeah, this one also, if you write it wrong, that should be a problem, right? So locate the XD, ZF, and also XB, right? And then what is the next step?
The XB.
Yeah, okay. And then,
Then after I find the ZF,
right, these points, okay. Okay, I think that's all, yeah. Next, yeah, after you find the XD, XF, and XB, and then what is the next steps?
Find the Q line.
Okay, how you can the Q line? How can you find the Q line? Okay, in Q line, remember we have to find the slope, yeah? What is the slope? Q divided by Q minus 1, yeah? Check my sorry, check my formula. Wait. Q minus Q1. Q divided by Q minus 1. Yeah? Check again the formula, yeah? Uh, yeah, wait. This one, and then the eraser. Okay. Uh, so this line shows a vertical one. So Dia, what do you think? Is it a saturated vapor or a saturated liquid? Anyone want to help? Anyone knows?
Saturated liquid, Mas.
Liquid or vapor? Liquid, yeah.
Yes.
A Q or Q minus 1 or Q divided by 1 minus Q, yeah? We need to check it.
It's Q over Q minus 1, ma'am.
Or Q over Q minus 1, yeah? So this is right, yeah, Helena?
Yes, ma'am, I think so.
Okay, yeah, so this is saturated liquid, because when Q is 1, which is saturated liquid, then the slope would be 1 divided 1 minus 1, yeah, or 1 over 0, which is infinity. And the slope for infinity, yeah, for linear graph is a vertical one. Okay, good. Thank you, Helena. And then, okay, so we got the Q line, and then what is the next step? Hadian? After we got the XD, XF, XB, and also the this one, the Q line, and what is the next step?
Intercept, Miss.
Yeah. Which one? Which intercept?
The ZF and XD.
Yeah. But before we find the intercept, we have to find the intercept for the minimum reflux. Yeah.
Oh, yeah, the minimum.
Okay. So we have to find this line first. Yeah, which is the minimum reflux, which is XD divided by RM plus 1. Okay.
Plus 1. Yes.
Okay, so later in your graph, construct this one, and then you want to read the scale. Okay, so if you want to read this scale, what is the scale? How you read the scale? How much is it, Hadian?
0.4.
0.4 is this one, so it should be more than 0.4.
Oh, how about 0.45, Miss?
0.45 is really in the middle. Yeah, is it in the middle? So maybe less than that. Yeah, maybe 0.
Okay, so maybe 0.44. Maybe?
Yeah. 0.44 is good. Okay, so everyone, if you say for example 0.444, if we look at with our eyes and then okay, this looks like okay, but yeah, okay, so that's that is correct. But for example, dia said, "Bubu, this looks like 0.43." That's fine as well, yeah. So the kesalahan parallax, the parallax error is fine, but if the line show you this, but you said, for example, "Bu, this is 0.4," that is wrong. Okay, so the plus minus that we see it is actually based on the parallax error. That's fine, but don't read too much, too much in errors there. Okay, right. So then you, for example, here you have 0.44 is actually XD. Your XD is 0.9, yeah, from the graph, for example. Divide by RM plus 1, yeah. Okay, then you can get the RM, yeah, and then you can get the reflux minimum. Okay, next, Dhamma. So what is the next step after you got the reflux minimum?
Find the I.
You want to find the I by find the reflux, your reflux. Okay, and yesterday we talked about the optimum reflux, so sometimes the reflux is between 1.25 to 1.5. So for example, this is an example that the reflux is 1.2. So then once you got the RM, you have to multiply it with 1.2 to get the R, right? And once you got the R, then you can find your intercept. Okay, and there you go. Next, maybe.
Bu,
Yeah. Okay, Kevin.
for the reflux, if you use 1.2 or 1.25, is it the same, Bu?
It is gonna be specified in the problem. Yeah. Okay.
Okay, Bu.
Usually it will be defined in the problem. Sometimes they use 1.25. Sometimes they said 1.1. Sometimes they said 1.2. Yeah. Check the problems.
If it's not given, what do you use, Bu?
You can put assume. You can put assumption 1.25 or 1.2. It's fine.
Okay, thank you, Bu.
Yeah. Ilham, once you got the intercept, what do you do? So once
Sorry, Bu.
Yeah, after you find the intercept, so Dama said you have to calculate the intercept. So let's we calculate the intercept, and you got this red line, yeah. And then you construct the red line. So this is the intercept, and then you can construct the red line, drawing the line from XD from to here. Okay, and then after that, what is your next step, Ilham?
I'm not sure.
Yeah, you want to find the stages for enriching section, the top section, ya, seksi bagian atas, ya, the enriching section. How you uh, call it? How you calculate it? So you want to start using your ruler from here, okay? Because this is the distillate, okay? And then you want to check the equilibrium. Okay, so this is it your first stage? Yeah, so if you use a complete condenser, a total condenser, yeah, if you use total condenser, then this is your stage one. Yeah, your stage one would be in the distillate, in the column. Okay, so this gonna be your okay. So can I maybe sketch this one a little bit? Or let me let me just erase some of them so I can draw. Okay. Okay, first you want to draw the column. So this is the distillate, yeah. So this is the distillate, which is the XD. Okay, and this one is your V, yeah, your vapor. Okay, and this is your first stage. Okay, so this one is your XD, which is this one. Okay, these points tell you the composition of the distillate. Okay, everyone. Yeah. So this graph connected to the graph. Yeah. Okay. Okay. So I have this one. What is the composition of vapor one? Back to here. What is the composition of the vapor one that leaving the tray one? How you read it, Ilham? You should read it too that way. Yeah. Okay, so this point, the Y tells you the coordinate for the composition of the vapor leaving tray 1. Okay?
Okay.
Yeah? Okay. So, Ilham, so what is the composition of the liquid that leaving the tray 1?
It's like 0.9.
Nope. You want to go that way, and then you read it the x-axis for these points, okay? Seperti membaca koordinat, ya. Seperti membaca koordinat. So this is the points. Baca ke bawah. Yeah, you read it that way, and then maybe around 0.8. Yeah, 0.8 something. Yeah, 0.81. So this is your x1. So the composition of y1 and x1 is actually represented in these points. Okay? Right. Okay. The next step. Now, maybe Kevin again. Kevin, how do you find the composition of the vapor leaving the tray 2?
The second triangle, Bu. Just drag it to the left.
Yeah.
Is that right?
Yeah. That's why you said that. Okay, so then you go to the operating line, yeah? You go to the operating line to get these points. Okay, so look at this one is in pairs. Yeah, look, this is in pairs. X pairs with the Y2. So this is the X and pairs with the Y2. And then again, how to get the liquid leaving the tray 2?
Just drag it down, Bu. Yeah,
Yeah. So then, yeah, yeah, which is, and then you go to the equilibrium one here, yeah. So this is the x2. Okay, so that's why these points tell you one equilibrium stage. Okay, so this is the equilibrium stage 1. This is equilibrium stage 2. This is the equilibrium stage 3. And this is the equilibrium stage 4. Okay, and then see, and you can see here that there is a feed over here, and then what you need to do is to stop it here for the enriching section, and then draw a line to the B, yeah, to the XB, that is for the stripping. Okay, and then you can want, and then maybe now you want to find the stripping section. Stage number 5 is the stripping section. Stage number 6 is the stripping section, and 7 and 8. Okay, so this tells you that this one in the tray you will need. So how much is the enriching section? How many stages? Nadifa, Nadifa. How much is the enriching section?
4 stages.
Good. How much is the stripping section? How many? The stripping section, the bottom section.
Without the partial reboiler, it would,
No. Without the partial reboiler.
without it's 3 then?
Yeah, this without is 3, right? And this one tell you about the partial reboiler. Okay, good. If Nadifa, if we use partial condenser, what is the number of stages in the distillation column?
For the whole thing, it would be 6.
Yep, it is 6, yeah. Okay, so good, Nadifa. So that means if you use a partial reboiler, this one gonna be one stage equilibrium would be on your, if you use partial condenser and partial reboiler, this one is gonna be your condenser, yeah? This is gonna be your condenser once this is stage. And this is gonna be number 2, 3, 4, 5, 6, 7 is your column, and number 8 is your reboiler. All right, everyone. So this is all the basic, and then later on, and after that we got about the heat duty, how to calculate heat duty, and after that it's done. And this is gonna be your exam for next week. Yeah, the basic.
May I ask?
Okay, Dama.
I'm sorry, I failed to catch up before about the stages. So there are 8 stages, and if we use reboiler and condenser, which one would be the reboiler and which one would be the condenser? 1 or 8?
Okay, there are 8 stages, yeah, but one stages at the bottom is always used for reboiler. Okay, because reboiler is one stage. Okay, so if I ask how many stages in the distillation column, and then you said 7 stages, because Nadifa said one stages, the last stages is used for reboiler. Did you get it? Because in the reboiler,
I see. And if it's a condenser, it would be not the stage number 1.
yeah, but in this case, the condenser is total condenser. See, there is no equilibrium in here. But Dama, if you use a partial condenser in the problem, your first stage is gonna be the condenser. So then your body, yeah, your distillation column only start from 2, 3, 4, 5, 6, 7. So it's only 6 stages.
Oh, I understand now. Okay,
Yeah.
ma'am. Thank you.
Okay. Yeah. Okay. Let's continue. We need to catch up with time as well. So, right. Let's have a look. What time is it? Okay, half an hour already. Okay, so I'm just gonna continue this one. This is total reflux. Okay, now I'm gonna let you know as well that this is a type. So sometimes in the distillation column we can specify. Sometimes we can miss. Yeah, there's some misdesign or different feed changing or something, changing feed and so on. So for example, here we have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, for example, this one we have 6. We have 8 enriching, and the feed is open. It's actually put it in stage 8. But sometimes, for some reason, maybe for the construction, we put it in 7 or 9, for example. Yeah, so we don't put the feed in the optimum condition. So what happened? So to explain that, let's have a look in this graph. This graph is more simplified. I took it from the Seder and Henley book. So yeah, maybe this one is more simple. Yeah. Let's look at this one. Okay. See, this is with the full condenser. With a full condenser and also a partial reboiler. So this tells you that the stage is a 5. So this is the ZF, and also this is the Q line. So this is the point P where from the XD to the intersection point, let's say. Yeah. So this one is the optimal stages. We have 1, 2, 3, 4, 5, where the 5 is the partial reboiler. Okay, so for some reason, for example, so this is the optimal feed stage location. Okay, and then look at the point B. Okay, what happened, for example, the feed stage location below the optimal stage. The feed stage location is below the optimal stage. What happened, for example, oh my goodness, oh my, in my distillation column, I put the feed stage on stage 5, let's say, okay, yeah? I only can do it, maybe it's open on the stage 5. What happened with my distillation column, for example? Okay, instead of stage 3, we put it for stage 5. So that means even it's actually in the enriching section is only up to stage 3 here. After the stage 5, it doesn't go to the stripping column. Yeah, it doesn't go to the stripping column. It still will follow the enriching section. So then, okay, this is what is enriching section, stage 1. This is stage 2 enriching section, stage 3 enriching section. There is still no feed, so still we'll go to enriching section, stage 4, stage 5 again enriching section, and then we see the feed. Okay, so then in stage 3, in stage 5, then there is the feed. If there is the feed there, then it gonna swift into the bottom line, yeah, to the bottom operating lines or to the stripping operating line, and then we can go, okay, so because this is the stripping operating line, okay, so this is okay, so this is the stage 6 and then the stage 7. So this tell you that if you don't have a optimal feed when you put it into the distillation column, that then you need, theoretically, you need 7 stages, while if you use a optimal one, you use 5 stages. Okay. This also happens if you put the stage is too early, yeah, just above the optimal stages. For example, we put the feed stage in, for example, in stage 2. Instead of stage 3, we put it in stage 2. So for here, we want to, okay, this is stage 1, okay, and then this stage 2, and then it will go straight into the bottom. Yeah, so the bottom section, then we will have stage 3 in the stripping, 5, 6, 7, 3, 2, 3, 4, 5 would be in the stripping section. Okay, so that's tell you that if you don't have a optimal feed stage sometimes, yeah, in the practice, because we have only maybe one distillation column, and then sometimes the feed is changing, or the composition is changing, so the feed stage also going to be changing, and we don't have the right equipment, and so that will result in non-optimal stages, or we need more stages. In practice, how we can get more stages, it's very difficult. Yeah, we can't just uh, make a turn down, yeah, shut down the plant and then change the distillation column. It's really not practical. So sometimes we need to change the reflux ratio, or the composition, or the amount of distillate that we can get. Sometimes that would be the play around, yeah. But how to get that, it is more like problem solving. Yeah, they deal, the engineer in the field deals with the fluctuation of composition, feed, for example, or a changing in maybe one tray is broken, and then it just will leave it out, so then the tray actually -1, less than 1, and so on. All right. Okay. So again, yeah. So this one, we have this continue. Okay. So then I'm gonna just continue the next one, the reflux ratio also from yesterday. Yeah. So around 1.25. Okay. Now one more is actually the efficiency. Yeah. So what is actually the efficiency, or what is the stages? So see, if you remember back to the explanation again, back to here, we always need to correlate all the graph with the schematic of distillation column. Yeah, in the graph, for example, this is stage N. There would be always there would be always mixing between the L, yeah, the liquid from the top, and also the X from the previous one, yeah, and also from a mixture as well from the vapor from the back, from the bottom, and also the composition of the vapor. Yeah, and then they just kind of, so there is mixing between vapor from the bottom and also liquid from the top, and then they will mix together, and the mixing must be intimate enough to allow diffusion between the vapor and liquid phase would be react, and then it's gonna reach equilibrium. Of course, this should require time, and also it also depend on the equipment. Okay, few weeks ago I tell you it looks like a tray, yeah, like in the steamer, yeah, like in the steamer in your home, in the kitchen. It's in the steamer, there they have a hole on it, yeah, and then you vaporize vapor, or you vaporize the hot water, and then the vapor will comes up. Yeah, it looks like that. Okay, the vapor that comes up there will contact with the liquid phase, and there should be intimate diffusion, yeah, and then to reach equilibrium. And once you got the equilibrium, you want to lift them, and you want to lift the vapor with new composition. Let's say YN and L, which is XN. Yeah. So then, and after equilibrium, the vapor phase and the liquid is separated. Okay, so vaporize up to the preceding stages, and the liquid will flow down to the next stages at the bottom. Right. So Based in this explanation, so that means 100% efficiency would be about 100% equilibrium. Yeah, if it is 100% equilibrium, that your stages is 100%. But sometimes the efficiency is not 100%. Of course, the mostly maybe about 70% or 80%. So then, so later, if you want to, if they even if in the problem they said the actual stages would be uh, the the theoretical stages divided by efficiency. Yeah, for example, if the theoretical is let's say 10, for example, okay, so for example efficiency, for example 80%. Okay, so what is the actual? So this is simple, yeah. The actual stages would be 10 10 divided by 80%. So that's about 10 divided by 0.8, so around 12.3, 12.5, yeah. Or and then you round it up to the higher number, which is 13. Okay, so in the real ones, when you want to construct the distillation column, you don't construct only 10, but you construct 13. This to allow us to deal with the efficiency. Okay, up to here, any question? Right. Okay, okay. So so the actual stages and the efficiency, it should be designed as good as possible, and also the good equilibrium should be able to mix the liquid vapor to reach the equilibrium. And also stage efficiency is denoted in percentage. It's actually the value to measure how close it is to reach equilibrium. Yeah, the higher the value, the close it gets to the equilibrium. Yeah, so efficiency is, while it's influenced by the equipment and configuration, is also depend on the flow. Yeah, the flow rate, the flow profile, is it turbulent or yes, the flow profile. Yeah, how much is the liquid, how much is the vapor. Okay, so efficiency is a complex function of tray design, fluid properties, and also flow pattern. And for binary distillation, particularly for close to boiling mixture, viscosity is actually when it is low viscosity. For well-designed tray, optimal operating condition is around 70% or more. Yeah. I think there should be some graph here. Okay, again from the book. This is the overall efficiency, and it actually correlates to the viscosity. Yeah, if you have a higher viscosity for a very viscous product, that a thick liquid, yeah, liquid yang kental, that is you have very low efficiency. But if you're dealing with distillation of hydrocarbon, look at the circle, yeah, the white circle here, around here. It depends from less than 90% up to 90%, yeah, or maybe around, yeah, around this one. Okay, so it really depends. So between 60, 40, or sometimes it can only 8% if this is for absorption of hydrocarbon. Okay, this one is also another one, a commercial hydrocarbon, chlorinated hydrocarbon uh, alcohol fractionation, laboratory fractionation of ethanol, and so on, is also varied between 80, yeah, to maybe 50% for very low volatility. Yeah, the relative volatility of those key components should be yeah, quite low. Right. So that's okay. So we have done the. We should know how to construct the equilibrium stage. We also know the feed and also for the pressure. Again, pressure usually should be low, so it should be low than 50 bar, of course. And the pressure, like if you remember about PXY diagram, if you go to higher pressure, you have quite narrow the separation. So it's better to have a low pressure as possible. And for the feed that is not sensitive to temperature, the pressure is chosen based on the availability of cooling media on the condenser. Yeah. Okay, so this is an example algorithm. The cooling media. So usually, if we know the distillate and the bottom composition, we have to calculate the bubble point, yeah, or pressure of the distillate. So at around the cooling water temperature, yeah, if the cooling water, for example, 22 to 25 to 35, let's say, so we need the distillate maybe around 49, for example, okay? And then we check the pressure dew point and so on, yeah? And for the bottom pressure, how we calculate it, we need to choose also the bottom pressure and then, yeah, about the bubble point as well, okay? Or but if the pressure is too low, then we can or we can use a refrigerant, yeah, pendingin, for that one there. Okay. Okay, so the next one. Okay, now this is, yeah, this one is the one that we talk about a few times about the difference between partial and total condenser. Okay, look at this one. The upper graph, is this total condenser or partial condenser?
Total, Bu.
Yeah, good. So this is a total. If this is a total condenser, if this is your XD, yeah, if this is your, let's say this is your XD there. So what is this? This is gonna be your first stage, yeah. So then if you read it there, this is gonna be your Y1. Okay, so this is gonna be your Y1. So this is gonna be your tray 1, and then this is your Y1, and your Y1 would be the same with XD because it is quite similar. Okay. Okay, so that is the total. Now let's use a different color. Okay. Now how about this one? This one is a partial. Partial. Yeah. In the partial condenser, the product is in vapor. Yeah, usually. Usually the so in the partial, this one is gonna be in the partial one, this is gonna be your condenser. Yeah, this is also gonna be your partial condensation. This composition would be your partial condenser. Condenser. Okay, so where is the y1? So this is gonna be your y1. Yeah, and this is gonna be your x. So your sorry, don't write it y1. Maybe okay, let's say so this is gonna be your stage 1. Yeah, this is gonna be your these points. Okay, so then maybe so this is gonna be the y of the condenser. This is would be x from condenser. Okay, and if this is your stage 1, so where is your y1 then? Sorry. So where is your y1 then?
The second triangle, Bu.
Yeah, okay. So that's good. Okay. So now because we're looking at here, so your y1, you want to look at the x1, the x from condenser to here, and you want to go that one, and then check to here. This one, this is the one that you're looking at the partial condenser, yeah. And then this is going to be the x1 in the partial condenser, the pink one. Okay. Can you see the difference? Okay. Anyone want to have a question? Let me pause in this graph. The difference between total and partial. Dia, are you starting to get it?
Yes, Bu, a little.
Okay. How about Dhamma or Ilham? Can you start to get it? The difference between partial and the total condenser?
Perhaps, ma'am. Trying.
Try to? Okay, yeah. Maybe sometimes you maybe in the tutorial, or if your friends asking, oh, okay, so okay, the total, the first triangle is your total, second triangle is your partial. Yeah, maybe that is the practical way. Yeah, but the concept in the partial condenser, this first points, or in the first triangle, is used for partial condenser. Okay, we really need this concept because later on, for example, how if we change it into partial condenser, how if we change it into the boiler, we change it into steam, for example. Later I will explain, yeah, how to do that. Knowing the concept is actually much better. Okay, okay, right. Okay, so here again, I always copied again from the book, so to make sure that we use it from the book, yeah. So there is a total condenser, the condenser type, where we have all of the vapor is condensed into a liquid, and after that we have a drum, actually, and then there is a valve, some of them going back into the liquid and some of them going to the distillate. Okay, the second one is the this one is partial condenser. Yeah, in partial condenser we could just maybe some of the vapor, and then we leave it equilibrium in here. So here there is an equilibrium. Yeah, this is one stage of equilibrium where the vapor we collect it as a distillate, and then all the liquid is turned back into the distillation column. This is a partial condenser. And also there is a mixed condenser. In the mixed condenser, we have the vapor distillate. We take all of the vapor distillate from some of the sudden condensation, and then also some of the liquid distillate also we get it. Okay, so here this one is also Okay, so for example, also this one is a schematic, yeah, a schematic mole fraction of hexane in the vapor and also in the liquid. If you, let's say you have three stages there, this one is used for partial condenser, yeah, this one there, this was used for partial reboiler, then here you have only one plate, yeah. I suggest when you learn between the graph, always also sketch the distillation column to make sure that we know the point. Yeah. For example, this is the XD. Yeah, this one XD 0.8. It goes to partial condenser. So then it will leave with XR. Yeah. So this is the XR, the composition of XR. Read it to here because X we have to read it to the horizontal one, and then we go to the operating line, and then to know the composition of the vapor, go to here, so X1 and Y1 there, yeah, and then to know the composition of YB, we use also partial, we use also this one, yeah, the operating column, and then you get the partial reboiler. An example from the book. Okay, this is some rule of thumb that the total condenser for the reflux dam is around 14.8 megapascal. The partial condenser is between 14.8 to 2.55. Again, the why we use this is actually based on the vapor liquid equilibrium. Yeah, we have to check which one is the bubble temperature or which one is the dew temperature. Okay, and then the mixed condenser should can provide both vapor and the liquid distillate. Right, now let's go back to here. Let's look at the bottom. There are also two types as well. The partial reboiler and the total reboiler, but we mostly use partial reboiler in almost almost every this one, yeah, every distillation column, because from the partial reboiler we can have lower XB. Okay, look at this one. What is this one? Is it a partial or a total reboiler?
Partial.
Okay, Kevin. This is partial. Okay. Let's have a look. So if this is XB, where is XB? This one, yeah? Okay, this is XB. Okay. And then it correlates to Y reboiler, yeah? Y reboiler. So this is the Y reboiler. Where is the X? XN. How to read the XN? We want to read the XN, so we want to find, so then we go to this one, to the operating line, yeah, to the operating line to find the XN. So this one is XN from these points, yeah, okay. Okay, so then again, we can go back. So here, this is the YR, okay, and then YR, maybe YR go to that one there, YR, okay, so this is the XN. Okay, so then YR and XN is actually paired in operating line. So to find the YN, which is paired in operating line, then we use XN. There, go to the operating line. Okay. How to get the vapor leaving out the tray N? What should we do? Then we want to, if we want to find which one is the YN, or the vapor that leaving tray N, then we have to read it to the equilibrium line there, and then read it to that side. Okay, so this is gonna be your YN in the partial reboiler. Okay, one more. Let's find. How about this one? This is a total, yeah, total condenser. In the total condenser, your XB is actually this one, yeah, and then all of your B you vaporize into the vapor. Okay, so then this gonna be your vapor there. So because this so that means the composition of XB, all of your XB, if you vaporize it, that would be your vapor here. Okay, that one there. That would be your reboiler. Okay, so that would be your reboiler, and then you use the similar way. Then this gonna be your stage to get the liquid. Also, which one? The liquid. You also get this one. Also tells you the liquid, yeah, in the last stage. So this one is actually the XN as well. XN. Okay, so in summing up, that in a partial reboiler, if it is N, this is let you know that N plus 1. For one is used for reboiler, but for in total reboiler, there's only N. But mostly, we always use a partial reboiler because it's easier. We get lower XP, and then we can use all the vapor to heat it up, and then to run the distillation column. Yeah. Okay. So this is the schematic of the reboiler. Oops. Let me check. This one, the reboiler for the plant size distillation column. The first one is a kettle type. Maybe you have learned the kettle type in heat exchanger, yeah, perpindahan panas. Heat exchangers, you would see numbers of exchangers. We can use steam for the heat heat support there, and then this is the water, yeah. This is the this is the liquid, and then it goes to the which one, to the tube there, and then some of them will vaporize, some of them will have a liquid new composition, and then we tap it out at the bottom. This one, the second one, is a Thermo Siphon type reboiler, where all the reboiler liquid also tapped. Some of them is tapped with the bottom, yeah, with here with the bottom sump. So still we'll use composition of this one, and then this one is a reboiler liquid also, and then withdrawn from the bottle downcomer. Yeah, it's quite similar to this one. So this is the liquid came from the previous stages, but then we also have the bottom there. Okay, now the next one, once we know the condenser and the reboiler, we also need to calculate the heat duty. For the heat duty, it based on the uh, energy balance, mass and energy balance, to calculate the heat duty between the condenser and the reboiler. Okay, I may not have enough time to explain this, so we may want to have a practice also explanation from book race and also the assistance on the tutorial. Yeah, so we can learn using really just real example. Here is actually for the heat duty condenser and reboiler. You can check, for example, the energy comes to the condenser equal to energy out. Yeah, energy in equal to energy out. So V multiply with HV equal to Q plus LHL plus DHD. Yeah, okay. So you can try to check that. Also, you have learned about mass and energy balance, and also here about the condenser. Again, the liquid plus H multiply with HL plus the QB would be equal to the output. So let me write it maybe a little bit slowly here. So here for the condenser, okay, so V HV plus sorry, equal, yeah, equal uh, equal to this one. We need to add the Q condenser plus L H L plus D H H D. Yeah, this one, and then you can write it similar to the reboiler, but in the reboiler you have to add the Q, yeah, to vaporize the vapor and also the liquid. So here L multiply with HP HL plus with the Q of the reboiler, for example, that's equal to V HL plus B H. Okay, this is the simple way to write it. Okay, so here this is also an example. There I took it from the book, but they don't have the schematic, so we're gonna use still the schematic. So it's actually tell you that this is the energy balance, yeah, of all of them. The feed from the feed of the heat plus the reboiler that we heat up from the bottom equal to distillate multiply with the enthalpy in the distillate plus the enthalpy in the bottom multiply with the liquid in the bottom, and then also the Q condenser, and also maybe there is if we have a Q loss. Okay, so in energy balance in the total condenser, we can summarize it as a D multiply with R plus 1 multiply with the energy of evaporate. So this is the delta H is actually average molar heat of vaporization of the two components separated. So if we have a mole fraction of A and mole fraction of B, so you have to check also mole fraction of A multiply with the heat evaporation of A plus mole fraction of B multiply with enthalpy of vapor of B. So the approach is the ideal approach, yeah. Okay, and then again, so this is also for partial reboiler. The B or the liquid or the flow rate of B multiplied the vapor phi B, yeah, and then multiply again with the vaporization. Okay, so here also if there's also calculation how to calculate the for example, we use steam to heat it up the reboiler. There's some steam rate, yeah, this is similar to utility system. You may want to have a look to check it. And also here the cooling water for the condenser, if you want to calculate the cooling water for the condenser, the specific heat of water and also the temperature out of the water and in, yeah, you can have a look at later. Okay, so yeah, so one more actually, sometimes we have we call it open steam, yeah, we can open steam. This is for two components when the A is a component A and B is actually water. Okay, if the component A and B is water, sometimes we just add the steam, yeah, sometimes we just add the steam, which is 100% water, which is 100% B, yeah, 100% B or 0% A, yeah, or the X, if you see the XA is 0%, okay. So what happened if we use open steam? If you use open steam, you want to look at the pairs. You want to look at don't worry, yeah, just look at the pairs between here, yeah, the pairs that correlates, yeah, yang berlawanan is actually a operating line. Okay, so to find the points of the operating line, let's look at the pair. Okay, if you look at the pair here, this is what is the composition of the A that leaving out the distillation column? XB, yeah, X of the bottom, yeah. Okay, so this is XB. Okay, what is the composition of A that passing in this stream, in the steam? What is the composition of A? Of the vapor. What is the composition of the vapor for the steam? Component A, B is the steam. Okay, come on. What's the composition of A? If the steam is 100%, so what is the composition of A? Okay, I'm gonna check again, yeah, from the beginning, yeah. So we have two components usually for the open steam. First is component A. It can be maybe ethanol, it can be maybe methanol, or maybe organic compound, or I don't know, yeah, maybe just a component. And the component is water, or H2O. So B component B is H2O. So instead of we have a partial reboiler, maybe we can just put the steam as the reboiler, because in steam there's a lot of energy, right? There's a vapor and then there's energies, and we can put the heat to heat it up all the streams, yeah. So here we put the steam, which is actually 100% B. So what is the composition of A in the steam?
0, ma'am?
Yeah, that's good. So that is 0. Yeah. Okay, good, Helena. So that is 0. Okay, and because 0, so this is 0, yeah. So the composition of the steam, this is the Y, yeah, and then so this is the steam, 0. Yeah. So the pair between 0 and also the xb, then it goes to this point. Yeah. So instead, xb is around here, then your last point for the stripping section is in this section. All right. Okay. Okay. So, but what happened then? Okay. So to know that the one that leaving the tray X, tray N, let's say. Yeah. Then you want to find. I don't know. Yeah. You want to find the composition. So this is actually I'm gonna write it back as a red, so it's easier. Maybe. So again, so this if this is tray N, then this is your, for example, this is your tray N. Okay. So then this is the composition that leaving the tray N. Okay. For example, okay, so this is your stage. Then maybe you want to construct from the top, yeah, and then your line go to that way. So this is your XB. Okay, so this is composition. But actually, sometimes the real composition, maybe if you look at here, this is the one that the composition that leaving out the tray N would be maybe this one. Yeah, this is the XN. And this one is YN. Yeah, this one you can look at. Now the question is, but this one is more than XB. Yeah, that's fine, because this is more this is less than XB. It's just not similar, but that's fine. But this is just the calculation to get the pairs. Yeah, the pairs of your your later for the stripping section. Okay. We can go back here. We have still time on Thursday. Then maybe we can have also another session outside the class, maybe at night, yeah, maybe, or you can choose the time, and then for more tutorials with Book Grace or even with me. Okay. Another one. Book Grace, are you there? Okay. Let me check. Yeah, I think she didn't know the. Let me check a little bit. I think I need to. Okay. 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 Anyway, if we can't finish the practice while we're waiting for Book Grace, we can continue this one, yeah. Okay. Okay, now the next one is we want to use a side stream. Yeah, we want to use a side stream. This is 10.15, so maybe just a little bit. This is also the same with the side stream. So this is a type of side stream. So what happened with the side stream? When the size, because we know that in side stream, do you know what is the gradient? Do you know what is the gradient of this one? The gradient of operating line. So what is the gradient of operating line? The gradient is actually L over V. Yeah, if you remember. the gradient is actually L over V. So what happened if you have if you withdraw some of them, kalau sebagian diambil ya, if you withdraw some of them, then your liquid gonna be smaller ya, akan berkurang ya, your liquid's gonna decrease. Let's say for example you have a gradient 1/1, okay, and then you have a side stream. I want to get maybe 20% of the product of this tray. So for example, this is tray 1, 2, 3, and 4. Okay, let's say I want to withdraw some of the liquid in tray 1, or some of the vapor in the tray 1. Okay, so this tells you that this is if you draw the liquid, then this maybe become we draw for example 20%. Okay, then so then your new gradient become 0.8 divided by 1. Okay, so that's an example. Okay, and also sometimes the side stream always depends on also the phase that you take it, bergantung dari fasa yang diambil ya. For example here this one they take the S1 as a vapor or as a liquid. Look at the Q line and then check, is it vertical or horizontal? Is it vertical? Yeah, so what is the phase? Fasanya vapor or liquid?
Liquid, ma'am.
Yeah, so then we draw the liquid. Yeah, so that means for example here 1 we only withdraw 0.2, then become 0.1. Okay, then we can construct a new percentage. Yeah, we can construct new gradient with the new gradient there, and then we can get the new gradient there. Okay, and for example this is, we have a feed. Yeah, and the feed is actually a mixture of vapor and a mixture of liquid. Okay, so then you have your new one. Okay, for example, and then okay, and after that I have another side stream over here. Okay, and then we go check again from the bottom there. I want to take all of the vapor, maybe half of the vapor for example, and we took out the vapor, and then it's up to maybe this point, and then we can connect it those two points to get that one. Yeah, so the influence of side stream, it will affect the gradient of the operating line. Yeah, so if we have a number of side streams like this, then we have maybe a segment. Yeah, it's not enriching again, but it would be maybe the enriching have maybe have two segment, and also the bottom, the stripping also has two segment. Yeah. Let me check one more with Grace. Okay, she's not here yet. All right then, maybe I'll do the latihan. Okay, another one. What happened with the multiple feed? Yeah, the multiple feed is the same. Yeah, it also depends on the phase, and also we want to add the multiple feed. Yeah, it also depends on the, and also it gonna change the gradient from L to V. Yeah, the change between the L and V, it gonna change as well. But all the calculation, I think we have some examples later on to check what happened if we add the feed or the side stream. Side stream and multiple feed. So then here you have to do some combination, yeah, between the, for example, you have the feed, and then you take it out with the side stream, and then you have another feed. Yeah, this is just some calculation, but the basic concept is the gradient L over V, so that you change your gradient L over V. Okay, so summary, In summary, the binary liquid vapor mixture, it can be separated economically into two nearly pure products by distillation, provided the relative volatility is greater than 0.5. And distillation is the most mature and also widely used separation operation, and also with the design procedure and operation practice well established. Yeah, the purity of the products, of course, depend on the number of equilibrium stages. Sometimes if you have 10 stages compared to 20 stages, of course, the purity would be higher with the 20 stages. In some products, sometimes it can go to more than 99 stages. Yeah, even in the, it's not for distillation, but I have in earlier this year I learned a lot about separation of rare earth metal. It's not using distillation, but it's using extraction. But in extraction itself, because the component is really similar in the relative separation, we can make up to 90 stages for extraction. So there's a lot of uh, mixel settler, yeah, for extraction. So yeah, so see, that depends. So this is going to be the challenges for us if you want to have a pure product from raw materials for the separation. It really depends on a number of equilibrium stages. Yeah. In the rectifying section above the feed entry, and also in the stripping section below the feed entry, and also the reflux ratio. Yeah, we can also play around with the reflux ratio if we have a similar stages. If we have a high reflux ratio, we can have a better composition, but maybe very less product that we get. Yeah, but if we have a low reflux ratio, the purity may not be good, but with also with more products. So it really trade off. What do you want? What is your purity? What is your amount? Yeah, the output of your distillation column. What is your capacity? Maybe later on it would be connected to the next stages of your process. Yeah, it really depends. All right, and then the next one, and then distillation actually is most commonly conducted in trade. Looks like in your steamer at home, ya, pengkukus ya, di kukusan, in a trade store, and then also it can equip with sieve, ayakan atau steamer, ya, and also a tray atau valve tray. And most distillation tower are equipped with condenser, and also it's cooled with cooling water, and also that's to provide reflux, and then also reboiler, heated with steam to provide a boil up. And a McCabe-Thiel graphical method is a method to determining stage and reflux requirement, assumes that constant molar overflow is valid. So, okay. I have a quiz just for your curiosity. Yeah, we have a mixture of methane and ethane. It should be separated by distillation, and explain why water cannot be used as a coolant in the condenser. And what would you choose as a coolant? Right. Okay. Maybe you want to think a little bit why this happens.
Can I try, Bu?
Yeah, okay, Kevin.
Wait. I'm also kind of confused with it. But like, my run of thought is just because methane and ethane normally run in like really low temperatures, and water will turn into ice, I guess. That's why you can't use water, but I don't know, Bu.
Yeah, that's right. You have to be more confident. Of course, you need to check. Yeah. Of course, that's right. That's the correct answer. Of course, methane and ethane is in a gas phase. Yeah, you need to be a cryogenic distillation. Good. So if you use water, then the temperature should be around 45 degree. Yeah. So even if you cool it down to 35, it's still in a gas phase, right? That is the this is the correct answer. So what would you choose as a coolant then?
I have no idea, Bu.
Okay. We usually use refrigerant. There's a number of refrigerants that can be really low, ethylene glycol or maybe more of that. Yeah, maybe ethylene glycol is up to one, maybe few degrees Celsius below zero. But for methane and ethane is actually very low, like minus 200 minus 100. So there should be a very low. Uh, coolant for that. Yeah. Okay. Thank you. Um, the next one. Why economic trade-off exists between the number of trays and the reflux ratio? Anyone want to try to answer? This is actually gonna be connected with our oral exam, oral presentation, a group presentation, because we're gonna really learn and you're gonna be assessed for your design knowledge, yeah, your design knowledge and also engineering judgment. So as a chemical engineer, you don't only calculate. You don't only calculate. Okay, my calculation is equilibrium tray is maybe stage only 10. Yeah, we don't want that. That's not enough. We want to build and make it possible, and it also need to be, it should be economically, and even it should be safe, and also it should be have a good impact for the environment as well. Yeah. So economic trade-off. Why the economic trade-off exists between the number of trays and also the reflux ratio? Who want to try to answer? Maybe Nadifa? Nadifa, Nadira? Which one?
So I think
Oh,
um,
Nadifa.
for the number of trees, as the n increases, the capital costs will also increase as we need to install more trays. Whereas for the reflux ratio, as it increases, the operating cost for the condenser will be increased. As
If the reflux ratio increase, and then
the operating cost for the condenser will increase.
okay, yeah, that's right. Okay, so it really depend on the judgment, yeah, of us as an engineer, and also the information from the client, from the client, what they want. Uh, is it better to install more tray so you have a low reflux ratio, but you have to install a higher tower, yeah, a higher tower, or have a little bit low tray, but then uh, you need to play around with the reflux ratio, but then your day-to-day costs, your operating costs gonna increase. Okay, yeah, so that's why we have to find the optimum one, and the optimum one is around 1.2 of the reflux ratio, your minimum. Yeah. Okay, thank you, Nadisa. All right, that is the end of the slideshow for today. So also the end of the lecture, and we still have half an hour. So while I'll contact Bu Grace. I'll show you the latihan, yeah. You can try. Maybe put it there. No. Which one is it? So okay. Give me 1 second. Okay. Do you want? Maybe you want to do it on you. Maybe you can screenshot them and then put it on the Word, yeah, Microsoft Word, and then you can use insert line and so on. Okay. Or maybe you can also use my screen to sketch it, yeah, later. Okay, let's have a look at this one. Latihan, ya. Oops, wait a little bit. Okay, so let me full screen. Where is it? Okay, let me put it, let me share screen and this one. Okay. Okay, still Indonesian, yeah, but that's fine, so in bahasa Indonesia. Okay, so in your graph, try to do this. Okay, anyone? Can you see my
Bu,
screen?
sorry, Bu.
Yeah?
I think you're sharing the wrong
Oh,
PPT. It's the end of slideshow one, Bu.
oh, okay. So how to sketch, how to share them? How about this one? Can you see it?
Yes, Bu.
Okay, yeah. Everyone, you can have a discussion, yeah, with your friends. I will leave the this one here so you can have the discussion. In English or in Bahasa Indonesia, that's fine. Okay? Everyone, hello, hello.
Yes, Bu.
Okay, okay. Kevin, please lead the discussion. Bye-bye.
Okay, Bu. Thank you, Bu.
Thank you, Bu.
Thank you, Bu.
Hello. Do we do it here?
I guess.
Dude, it's still recording, so be careful what you talk about here, guys.
Oh my.
Okay, everyone, before I leaving this my room, should I pause the recording?
I think, yeah.
Okay,
Yes, Bu.
pause the recording. Yeah. Okay. Okay. Let's have a look. Can you share screen, Nadifa?
Yes, Bu.
Okay. Ooh. Right. Okay. Okay. So the feed is 100 kilomole. ZF is 0.4, right? XB, right. Let me check the point. Let me check the graph. One of the tips, we always look at the graph. Yeah. Can you go back to the? What is the application, Nadifa? What is the application that you use to write it down?
I'm just using notes, Ibu.
Oh, no. Yeah. Okay. Oh, that's cool. Okay, go back to the graph. Okay. So that the XD is 0.9. Yeah. Okay. Good. Okay. Next. XB. You didn't put the XB yet.
Not yet.
Okay. Good. Okay. Go back. Okay. Up. Go back. Just look at the graph then. Okay. Yeah, that's right. And then the Q line is liquid. Yeah, saturated liquid. Yeah.
Yeah, it's
Okay.
vertical.
Okay. Good. And then you're trying to find the intercept, right? And then so let's read together, everyone. So what is the intercept of the minimum reflux? So you may want to let me annotate how to do the annotation. Pure option
0.415, perhaps,
so
because
0.42, 0.45, so for about 0.441, yeah. Is that
I think 0.42.
2? Because the scale is 0. Because the scale is actually from 0.4 to 0.6, isn't it? The big scale. So one hop of this small square would be around 0.4, yeah, 0.04, isn't it? So that 0.2, around 0.2. Wait. I would like to annotate. I couldn't see my annotation. How do you know how to check annotation? Where is it? Option. No, yeah. Oh, annotate. Yeah. I got it. Okay. Let me write it. So from here to there is 0. Can I 0.2? Okay, so that means from here to 0.2, so one small block there would be about 0.05, isn't it? Because you divided 5.
0.04, Miss.
Yeah, it's 0.04. So because you're around half of the small blocks, then it's actually 0.02. So that means your intercept over here would be around 0.42. Yeah. Okay. And once you got 0.42 for the intercept, you may want to find the reflux ratio. And after that, you can do the let me check your work. Oh yeah, good. 0.42, and then you got the reflux minimum is 114. Okay, and then your operating reflux, good, around 1.5, so 1.7. Okay, next. Now what you want to do, you want to find the new x here, a new intercept. So what is your new intercept? Not yet, yeah.
Not yet.
Okay, that's fine. So then the next stage is you want to find the new intercept, and then you can start to do the and you can draw. Okay. Okay. Thank you very much, Nadifa. You can close the screen because I'm gonna show you the answer. Okay. So well done. So that is the right one. So let's put it there. So this is the question. So the minimum reflux is 1.14, and if the reflux minimum is 1.5 of the operation reflux is the 1.5 of the reflux minimum, perkirakan jumlah tahap. Okay, so it is a little bit dense, yeah, I'm sorry, but it's actually just similar, make it easier. So okay, so from here, where is mine? Yeah. Okay, so we find the Q line. This is the XD, and then this is the XB, yeah. And then we find the I minimum, and then you got around 4. See, if you look at here, this goes to 0.41, yeah. But Nadifa, your right sketches show 0.42. That's fine, okay, because we just look at the line and then how good is it to draw the line. Okay, how about the others? When you do the drawing, Kevin, what number do you get when you got the minimum intercept?
I got 0.42 as well.
Oh, okay, all right. Okay then. How about the others? Fatia, Alisa?
I got 0.41.
Oh, 0.5. Okay. See those yeah, variation, that's fine. But if maybe someone get 0.39 or 0.44, for example, or they wrongly read the scale. Okay. The next, and then we this one, if it is 1.1 0.41, they got our minimum 1.5, but our findings said that before that it is 114. That's fine. And then after that, we look at the R and then check the new intercept. Okay, so this is now is the new intercept around 313. Yeah, 0.2, 0.24, 0.28, 0.313, around this one there. Yeah, so this is your, so your this should be less, yeah, should be this one, it should be can you see my arrow cursor? No.
Yes, ma'am.
Yes.
Okay, good. Okay, so this should be lower, yeah, this should be lower, so the line should be lower than this. Okay, and after that we got the XD, and then after that we can find the XB. and then also make the line over there. Okay, and this one there. So this is 1, 2, 3, 4. Almost, so the feed goes to the stage 4, and then this is stage 5. Yes, 5, 6, 7, 8, 9. Around 9 more steps, but we round it up to 10. Yeah, because we're gonna see the distillation column, so we should round it up to 10 steps. This one, yeah, this is just, it's really up to XB, but we have to round it up to to 9.3 steps. Okay, and then so then we have 9. If let me go. Is it a partial reboiler? A partial reboiler and also full condenser, yeah? The total condenser, isn't it? Maybe, yeah. Let's say just this one. So the last one is gonna be the reboiler. So then you have 9 stages. So then means you have 9 trays. All right. I'm gonna give this one also to the EduNext so you can have a look, and then I'll see you next week then. Okay. Before we finish, any questions? It looks easy on the answer, but when you do it by yourself, it's actually quite hard, and you have to have a little bit precision. So think about by yourself. Are you better using the app like Nadifa, or do you want to use pen and paper? It's really up to you. Yeah, just prepare the method that you want. Okay. Okay then. Thank you very much, and have a good weekend, everyone. Bye bye.
Thank you, ma'am.
Thank you, Bu.
Thank you, Bu.